Hey, so for today's lesson, we're going to talk about the development of atomic theories. I'll tell you the truth, I used to actually really not like this lesson. It was something I didn't enjoy teaching. But then I got more and more into loving the scientific method and kind of understanding what a scientific theory is. And then from there, I now actually just love this lesson, and I love how it shows the connection between technology and advancement there, and then our understanding of science, and then how theories change. The beauty of science is it's always wanting to be shown that it's wrong, so that theories can be changed and modified in order to match the evidence. So to start off, this image here is actually a really neat summary of different models that you're going to learn about, different theories and models. So I'm going to link it in the Edpuzzle so you can take a look at this and even print it off or whatever and see it. It's a free thing that's supplied, and it's really kind of cool. So anyways, let's move into this. So to start off, I want to talk about the nature of scientific theories because I think that that is just pivotal to understanding this and actually understanding science. There's kind of this whole thing of like, oh, it's just a theory when we talk about scientific theories, but theory in science does not mean the same thing that theory does in our everyday speech and use. So in science, here's what a theory is. It is a well-tested, broad explanation of a natural phenomenon. In everyday life, we often use the word theory to mean a hypothesis or educated guess, but a theory in the context of science is not simply a guess. It is an explanation based on extensive and repeated experimentation. So essentially, when we talk about theories in science, we're talking about a model, kind of a broad theory that at this point, every single bit of evidence that has been collected that is reputable agrees with that theory. Okay, so when we talk about theories in science, we're saying that it's a broad explanation that we can apply to different scenarios, but that everything we know so far agrees with this theory and fits into this theory. Because if it didn't, if something in science was discovered that didn't fit in with the theory, that showed the theory was wrong, well, then the theory changes, right? The theory has to be thrown out and a new theory is made, or the theory has to be modified in order to fit the new evidence that was found. So what you're going to see throughout this lesson is that we have a theory, and then it's discovered, hey, this is wrong because of this evidence, and then a new theory ends up being proposed. And then same thing again. So this is a lesson of how theories of the atom developed and changed as new scientific evidence was discovered as time went on. So we're going to start out with some ones that I actually wouldn't even call scientific theories, and I don't call them scientific theories because it was before the scientific method was used. You're going to learn more about this in grade 10, but it used to be that before the scientific method was kind of developed and used to find knowledge, what happened is people would just make simple observations and jump to conclusions without testing it. So Democritus is a great example, and he's actually responsible for the term atom. So he called the smallest form of matter atomos, which is changed into atom. And atomos means indivisible. It cannot be broken into smaller pieces. So that was from Democritus coming up with the idea of atomos. And what he basically kind of said or thought, his thought experiment, was that if you take something and you cut it in half, and then you cut it in half again, and then you cut it in half again, you keep on going and going and going and going, cutting in half over and over and over again, eventually you get to something so small that you cannot cut it anymore, and it's indivisible. That is the end. That is as far as you can cut it. And that's what he called the atom. Okay, things changed. And Aristotle proposed that everything was actually made of 4 essential elements. I should back up here. Of course, we know that atoms actually can be divided and are divisible, but this is kind of the first basis or start of our understanding of the idea of the atom. All right, so Aristotle thought that everything was made of 4 essential elements, so earth, fire, air, or water. And if you combine these in different quantities or different parts, then you would end up with different things. And you might think, oh, that's so silly. Well, if you think about, for example, a candle burning, right? A candle burns. You have, from the candle, fire being released, right? You have earth, which is like the soot that would come off the candle. If you put your fingers through it, you'd get black on your finger. Water is coming off of the fire. And then also you have the hot air rising from the candle as well. So you can see how people kind of believed this idea based on just watching things that were on fire or looking at different stuff and thinking, oh, it's like earth and water combined and whatever. So the idea was that everything was made up of these four essential elements. Now, of course, we understand now that this is not correct. This isn't real, right? That's not how everything is made. Instead, things are made out of the elements, the periodic table of elements. And we have different kinds of atoms that combine in fixed proportions to make all the stuff. Okay, now we're getting into the important guys, the ones that matter the most. So John Dalton. I like to call John Dalton Dalton Bolton. So I changed the start of his name to ball, as in the billiard ball model, which is what we call this model of the atom. Billiard ball, like a pool ball. So the idea from John Dalton is that all matter is made of small indivisible spheres called atoms, so very much like Democritus. But atoms cannot be created or destroyed. Atoms of the same element are identical in mass and size, and each element has an atom that's different from other elements. So this is good. So if you look at all atoms from an element, he thought that they were completely identical. We're going to find out later on that that's not perfectly true. And that atoms from one element are different than atoms from another element. That is completely true. And he had in his notebook all these different pictures of like different symbols that he called the different elements. And he said that compounds are created when atoms of different elements bond together. That sounds great. And this is called the billiard ball model. So again, what he did is he viewed atoms as being like these balls, right? And that each element had a different ball, a different sphere that it was made out of. And in an element, all of those balls or spheres, those atoms, were the same. So that's Bolton Dalton. Then from there, J.J. Thomson came along. And let me talk about the background for this. There was a development in kind of science technology that was called the cathode ray tube, or CRT. And what the cathode ray tube did is it actually created this line of particles that they could see and bend with magnets. And they discovered that these particles had a negative charge based on how they moved in magnetic fields. And we'll see if we can find a video of cathode ray tubes. The really old tube TVs and monitors, those are actually cathode ray tube technology. So what happens in those really big TVs and monitors is electrons are fired from the back to the screen that ends up lighting up and making the colors. That's how it works, is by firing these electrons. So anyways, they made this cathode ray tube and they saw that there were negative particles that were coming out. So they needed to figure out what these negative particles were because they weren't atoms, they were something smaller and with a negative charge. So they added in electrons to the model that already was there, Dalton. So what they said is, based on this evidence of these electrons, these negative particles in cathode ray tubes, we need to then modify the theory to include these negative particles. So what they did is J.J. Thomson came up with the idea of what's called the plum pudding model. And what this is plums are like the negative electrons that are in the pudding of like a positive particle pudding. Okay, so negatively charged electrons are stuck in a positively charged mass. Electrons were compared to plums in a plum pudding. So again, it's called the plum pudding model. So we kind of viewed it as there are these electrons, these little bits that are negative charge that are kind of embedded within a big sea of positive stuff. So that was J.J. Thomson. The next guy to come along, which was the biggest change to the idea of the atom, was Ernest Rutherford. And he did a few things, but the most important was what's called the gold foil experiment. And what he did is he fired alpha particles. Alpha particles are kind of like helium atoms, but he fired alpha particles at gold foil. And he expected that all of the alpha particles would just simply go through. This would be kind of similar to shooting an airsoft gun at like a Kleenex. You would expect that everything would just go through the Kleenex. But what he found is that some things actually were deflected or full on rebounded, bounced off of the gold foil. So like the alpha particle would come in and boom, bounce back here, or they would come in and boom, diverted a little bit to over here, when he expected everything to actually just go straight through. So this made him conclude or hypothesize, because this did not match the idea, the theory based on the plum pudding model is that everywhere should be the same. So no matter where you fire that alpha particle, it should go straight through. It shouldn't bounce back. So this changed the theory, the model of the atom, to include these really, really dense positive cores to the atoms, so that was what the alpha particle was hitting that made it bounce back or made it deflect, was this really, really dense and positive core. So when we talk about the atom, the idea is that most of it is actually completely empty space. But in the very middle of it, we have this really dense positive core. The analogy is if you put $1 in the middle of a football field, that dollar is the nucleus, the positive core. And then the rest of the football field is just empty space. And if you put a few flies buzzing around that football field, that's like the electrons moving around in the atom. But most of atoms are empty space, which is just crazy. It's crazy. So he predicted that all particles would pass through, but they did not. Some bounced or deflected. So atoms have a very dense and small nucleus containing positive protons. And then he also, on top of that, compared some masses of atoms and figured out that there must be particles that were as heavy as protons but didn't have a charge. And that resulted in the theory including neutrally charged neutrons. Get it? Neutrons, neutral, neutrons. Protons, positive, right? Starts with a P. Electrons orbit the nucleus. Most of the atom is actually just empty space. So we have this very dense nucleus in the middle that contains protons and neutrons. And then we have these negatively charged electrons that are moving around the nucleus. This is called the planetary model because it's like planets moving around, the sun, let's say. Although I don't love that idea because the next thing is called the solar system model. So let's just say it's like moons moving around a planet, but they're all the same distance away from it. So that's called the planetary model, and the idea is that electrons are moving around like planets. All right, Niels Bohr, the next guy, and he actually took a look and realized that electrons, when they got excited and then went down to a lower energy state, I'm talking Greek right now, but they let out light. So you can see this if you excite a gas. Like, for example, in something called a gas discharge tube. So if you put electricity through a gas, it makes light. If you put different substances in fire, it will actually cause the same thing, different colors of light to be released. This evidence resulted in Niels Bohr coming up with the idea, sorry, I just want to move this over so we can actually see it, coming up with the idea that electrons must be at different energy levels, and that would allow them to get excited and go up to a higher energy level and then to fall back down to a lower energy level, which results in letting out light. So imagine that someone's climbing up a ladder to a higher energy level and then they go down a slide. Yeah, and that going down the slide is going down to a lower energy level. And when they go down that slide, light is released if it's an electron. So it goes up in energy, getting energy from electricity or fire or whatever. And then as it goes back down the slide, it's releasing energy as light that you can see. So this evidence resulted in the Bohr model of the atom called the solar system model. And the idea is that electrons exist in what we call different energy levels. You can think about that as like heights from the nucleus, almost like floors in a building. So the first energy level, the first height, okay, can hold 2 electrons max. The next one can hold 8, then after that it's 8. So the idea is that electrons in an atom, they occupy the lowest energy possible. So if I have 2 electrons, they're going to go in that first energy level, 1, 2. If I have 3 electrons, 2 will go in the first and 1 will go in the second. We're actually going to get fully into drawing diagrams of these atoms. We're going to call them Bohr diagrams after Niels Bohr. But yeah, the way I remember Bohr is I think that Bohr is boring. And I think about the rings around the atom. Okay, so Bohr ring. So what you need to know for this, well, you need to know the name of the person, okay? You need to know the general idea of what the theory includes, and you need to know the name of the model as well as be able to identify a picture of the model. So you actually need to have quite a bit of knowledge about this. It's quite involved, but you need to know. So your notes, really good to study for this. Schrodinger. Schrodinger is just bizarre stuff. It's really a mixture of Schrodinger and Heisenberg that kind of came together to come up with this model. And the idea is that electrons don't actually exist in specific locations, but instead exist in these probability clouds. So instead, it's where electrons are most probable to be. And we can actually guess or calculate where electrons are most probable to be, and that's what gives us these, what we call orbitals around the atom. This is university level stuff, doing these calculations. So I actually dealt with doing some of these calculations or whatever to get the orbital shapes. It was pretty involved. It was like second or third year chemistry, I can't remember, but it's crazy stuff. So these orbitals are where electrons are 90% probable to be. And yeah, they have different energy levels, which is the number in front, and then different shapes. So S is a circle, P's are like these kind of dumbbell shapes. You don't have to know that. That doesn't matter. All you need to know is that Edwin Schrodinger gave us the quantum model, which is just all about electrons being where they're most probable to be in these probability clouds. All right, so what are we going to be using in grade 9? We're going to be using the Bohr model of the atom. We're going to focus on that. So we're going to look at atoms being in our energy levels, okay, around a very dense positive nucleus that has protons and neutrons. So each element has its own unique atom. Atoms have 3 subatomic particles inside of it. So we have protons that have a positive charge in the nucleus. P positive is the symbol we're going to use for protons. We have neutrons, which have a neutral charge and are in the nucleus, and we're going to use N with a 0 for that. It's a superscript up top 0, 0 meaning no charge. And then electrons have an E with a negative superscript, so that means it has a negative charge. So I have protons, neutrons, and electrons. Protons and neutrons are in the nucleus. Electrons are in energy levels around the nucleus. Here's an example of an atom. This is magnesium. So magnesium has 12 protons and 12 neutrons. The fact that magnesium has 12 protons is actually the thing that makes magnesium magnesium, but we're going to deal with that in a different lesson. Now, if I have 12 protons, in order for it to have a charge of 0, neutral charge, it needs to have 12 electrons. Okay, so protons and electrons in an atom are always going to be equal. Not in an ion, that's later, but in an atom, protons and electrons will be equal. So if I have 12 protons, I'm going to have 12 electrons. So 2 go in the first ring. I've got 10 left. 8 can fit in the second ring. Now that ring is filled up. And now I have 2 left over. They're going to go in the third ring, 1, 2. Okay. I don't have my pen plugged in to do a different example. I wish I did. I'm going to pause and get that. Okay, I'm back. Let's take a look at something like lithium. So let's say that I was trying to show what lithium is for a Bohr diagram. And we're going to go through, drawing Bohr diagrams later on. So this isn't super important to understand what's going on right now, just for you to see some models of the atom. So in the nucleus for lithium, I'm going to find my protons and my neutrons. Now lithium has 3 protons. And if you have a periodic table, maybe take a look and see how you think I figured that out. Little preview. And then it has 4 neutrons, typically. So now because lithium is an atom, right, it's going to have 3 electrons because the electrons have to match the protons. So in the first ring, the first energy level, I'm going to have my 2 electrons. 1, 2. I could show those with dots or as E negatives. Now I've got 1 electron left. It can't fit in the first ring because the first ring is full. So it's going to go, oh, ugly, ugly, ugly. It's going to go in the second ring. Can I do this? Oh, it's horrible. All right, second ring, and there's my 3rd electron. Anyways, we're going to have a whole lesson soon on how to draw Bohr diagrams, so we're not going to worry about that right now. All right, we're also going to learn a few quick laws that we need to know in order to move forward. So we're going to call this taking matter apart. We're going to actually watch this crash course video first. So here it is. And the rest. When compounds decompose, Elements are pure substances that cannot be decomposed. So if something decomposes, we know that it's a compound because it can break up then into smaller parts. Compounds can be broken up into those elements, and it's actually called a specific type of reaction that's called decomposition. That's important for you to know. So compounds can be chemically broken apart, okay, chemically broken apart into elements, and that process is called decomposition. Compounds can actually be chemically broken apart into even smaller compounds, but eventually if I keep on breaking it down, I'm going to get to elements, and that's a decomposition reaction. A law that you need to know about is the law of conservation of mass. This is incredibly important in chemistry. The law of conservation of mass states that mass can neither be created nor destroyed in a chemical reaction. Thus, the amount of matter cannot change. So whatever you put in for matter, that's what you get out, okay? The total mass of reactants will always equal the total mass of products in a chemical reaction. Now, this might not always be obvious because sometimes we're actually getting matter out of the air, right? It's either being released to the air or it's coming in from the air. But if we looked at a closed system, so matter is not leaving, not going in, it's always going to be conserved, and it always is conserved. So think about, for example, vinegar and baking soda. When you mix vinegar and baking soda, we have a lot of bubbling, and that's because carbon dioxide is being given off. So if we were to capture all that CO2 and weigh that as well as the sodium acetate that we have left over and everything else, it would turn out to be the same mass as what you put in. So in any chemical reaction, the mass of what you put in is the same as the mass of what you get out. Mass of reactants and products will always be equal. Incredibly important, and that's called the law of the conservation of mass. The other law that I want you to learn right away is the law of definite composition, and that's that a given chemical compound always contains its component elements in a fixed ratio. Okay, so it's always going to be a certain amount, okay, compared to like one element and the other element. So for example, for water, it's going to be H2O. So I have 2 hydrogens and 1 oxygen. And that's how I make water. It's always going to be a 2-to-1 ratio. That can't change. In fact, if I actually change the ratio to 2 and 2, right? So I have 2 hydrogens and 2 oxygen atoms. That's now something else. It's now hydrogen peroxide. It's a different compound. So for a given compound, the ratio between elements inside of it will always be the same. Has to be. Okay. Another example, let's say we're talking about something like ethanol, okay, alcohol, C2H5OH is the formula for alcohol. So for alcohol, I'm always going to have 2 carbon atoms, I'm going to have 6 hydrogen atoms, and 1 oxygen atom. And that ratio of 2 to 6 to 1 is how I get alcohol or ethanol. Okay, so that's the law of definite composition. We are all good. That is it for today. Have a good one.